March 28, 1945. Rhine River, Germany. 0700 Hours Oberst Heinrich Kruger, 46, Wehrmacht engineer commander, stood at the riverbank watching American engineers complete a bridge across the Rhine. His own unit had spent 3 days preparing a bridge site 15 kilometers south, planning, surveying, assembling materials. They hadn't started construction yet. Still preparing. The Americans started building yesterday morning. Now, 22 hours later, tanks were crossing a 300-foot bridge capable of supporting 40-ton vehicles. Kruger timed it with his watch. 22 hours from first component placed to first tank across. German doctrine estimated bridge construction time in weeks, not hours. A permanent bridge required surveying, foundation work, steel fabrication. Temporary bridges required specialized equipment transported by rail. Either way, river crossing capability took considerable time to establish. But the Americans weren't using German methods. They were using something called Bailey Bridge, prefabricated components assembled like children's blocks. No surveying, no foundations, no specialized equipment beyond standard engineering tools, just panels, pins, and determination. What Wehrmacht engineers learned studying captured Bailey Bridge components would convince many of them that German engineering, despite its reputation for excellence, had been outthought by simpler, more practical American design philosophy. Sometimes genius isn't complexity. Sometimes genius is elegant simplicity. By March 1945, Allied forces approached Germany's major rivers. The Rhine represented Germany's last natural barrier. Hitler ordered all bridges destroyed to delay Allied advance. German engineers demolished bridge after bridge as they retreated. Each demolished span represented months of construction, and thousands of tons of material now at the river bottom. German military bridge doctrine emphasized permanent or semi-permanent structures. Bridges were engineered for maximum load capacity and longevity. Construction required skilled engineers, heavy equipment, and considerable time. Temporary military bridges used pontoons or specialized modular systems like the Brückengerät B or Brückengerät J. These systems worked adequately but required specialized training and substantial transport. Capacity. The Bailey Bridge, developed by British civil engineer Donald Bailey in 1940, represented fundamentally different approach. Rather than optimize for load capacity or longevity, Bailey optimized for speed and simplicity. The bridge consisted of standardized prefabricated panels, each weighing 570 pounds, light enough for 6 men to carry. Panels connected with steel pins inserted by hand. No welding, no bolting, no specialized tools. The genius was modularity. Panels could be configured in single, double, or triple configurations vertically and horizontally. Need more strength? Add more panels. Need greater length? Add more sections. The same components built bridges from 30 feet to over 200 feet. Supporting loads from 12 tons to 70 tons. Construction method was equally innovative. Engineers assembled the bridge on one bank, parallel to the river. As sections completed, they were pushed or rolled across the gap using temporary rollers and winches. The bridge didn't need foundations or abutments meeting mid-river. It simply spanned the gap, supported by its own truss structure. The 9th U.S. Army captured its first intact Bailey Bridge components near Aachen in October 1944. Wehrmacht. Engineers examining the components were initially dismissive. The panels seemed flimsy compared to German bridge materials. The pin connections seemed inadequate for serious loads. German engineers calculated that such a bridge would collapse under typical military traffic. But as American engineer battalions demonstrated Bailey construction repeatedly through winter, in 1944-45, Wehrmacht engineers were forced to reconsider their assumptions. These inadequate bridges supported Sherman tanks, tank destroyers, heavy trucks, and artillery pieces without difficulty. More remarkably, American engineers built these bridges in timeframes German doctrine considered impossible. At the Rhine crossing in March 1945, Wehrmacht engineers observed American 291st Engineer Combat Battalion construct a 100-foot Bailey Bridge across the Rhine near Wessel. Construction began March 27th at 1800 hours. First vehicles crossed March 28th at 1600 hours. 22 hours for a bridge over one of Europe's major rivers. German engineer procedures for equivalent bridge would have required weeks. Site preparation alone took days. Foundation work required specialized equipment and skilled workers. Steel fabrication had to be precise. Assembly was sequential, each stage dependent on previous stages completing. Bailey construction parallelized everything. Multiple teams assembled panels simultaneously. As front sections pushed across the river, rear sections continued assembly. Specialized roles weren't necessary. Any trained engineer could perform any task. If one team encountered problems, other teams continued working. The system was resistant to disruption. Oberst Kruger's detailed report, written April 2, 1945, analyzed Bailey Bridge capabilities with professional admiration mixed with frustration. The report was recovered from Wehrmacht archives after the war. American Bailey Bridge demonstrates engineering philosophy fundamentally different from our own. We prioritize permanence, precision, optimization. They prioritize speed, simplicity, adaptability. Bailey Bridge is not optimized for any specific situation. It is adequate for all situations. This philosophy creates bridge that performs acceptably in all conditions rather than perfectly in specific conditions. The result is bridge that can be built by average engineers in hours rather than requiring expert engineers over weeks. The report continued with technical analysis. Bailey panels were deliberately over-engineered for most applications. A single-strength bridge could support 12 tons. Most applications needed only this capacity. But having standardized components that could be doubled or tripled for heavier loads meant engineers didn't need different bridge types for different situations. One system served all needs adequately. German bridge systems optimized for specific situations. Light bridges for infantry, medium bridges for light vehicles, heavy bridges for armor. Each system required different components, different training, different transport. This optimization created efficiency in specific circumstances, but complexity overall. Bailey's one-size-fits-most approach sacrificed optimal efficiency for universal applicability. American engineers carried Bailey components knowing they could bridge any gap they encountered. German engineers needed to anticipate requirements and bring appropriate equipment. When situations changed, Americans adapted. Germans often lacked appropriate equipment. The construction simplicity had profound implications. American engineer training emphasized Bailey Bridge construction. Every engineer battalion practiced repeatedly. Manuals detailed every step. Components were standardized, so experience on one bridge transferred completely to the next. This universal training meant any American engineer battalion could construct Bailey bridges competently. Excellence wasn't required. Competence was sufficient. German bridge construction required specialists. Engineers trained specifically in particular bridge types. Expertise mattered. This created excellence in execution, but vulnerability to casualties. Lose your bridge specialists, and bridge construction capability degraded dramatically. Bailey's simplicity meant losing individual engineers barely affected overall capability. The logistics advantages multiplied. Bailey components were compact and stackable. Panels loaded efficiently into trucks. Transport requirements per bridge were minimal. Components could be pre-positioned at multiple locations without dedicating massive transport capacity. German bridge equipment required specialized transport vehicles and significant cargo space. Most significantly, Bailey Bridge could be disassembled and reused. Complete a river crossing, move forward, dismantle the bridge, transport components forward, build another bridge. The same components built dozens of bridges during campaign. German bridges were generally permanent installations. Once built, components stayed there. This made German bridges either disposable or committed resources. The Bailey Bridge's tactical impact was decisive in 1945. As Allied forces advanced into Germany, rivers and canals crisscrossed their path. Each water obstacle could have delayed advance for days or weeks if engineers needed to construct permanent bridges. Instead, American engineers built Bailey bridges in hours, maintaining offensive momentum. Wehrmacht defenders couldn't destroy bridges faster than Americans built them. Demolishing a bridge took minutes. Building a German replacement took weeks. But building a Bailey bridge took less than a day. The equation favored offense dramatically. German demolitions became tactical delays rather than strategic barriers. After the war, Allied interrogators questioned German engineers about their assessment of Allied equipment and methods. Bailey Bridge consistently appeared in responses as equipment that most impressed German professionals. General Major Alfred Jacob, chief engineer for Army Group B, testified in 1946 interrogations. His assessment was candid. The Bailey Bridge was elegant solution to military bridge problem we failed to solve adequately. We understood that war demanded rapid bridge construction. Our solution was specialized modular systems that were faster than permanent bridges, but still complex. Americans solved the problem by making bridge construction so simple that speed became inevitable. They didn't make bridge construction faster. They made it easier. Ease created speed. This distinction is fundamental to understanding different engineering philosophies. Jacob's testimony continued with specific examples. At Remagen, when American forces captured Ludendorff Bridge intact, in early March 1945, German forces repeatedly attacked to destroy it. The bridge finally collapsed March 17 from combat damage and overuse. German commanders assumed this would halt American advance across the Rhine at that point for weeks, while a replacement bridge was constructed. Instead, American engineers built a Bailey Bridge 500 feet from the collapsed bridge and had it operational March 19, 2 days to restore Rhine crossing capability. German planning anticipated weeks. The impact on German defensive strategy was significant. Defensive doctrine relied partly on using river obstacles to force attackers into predictable crossing points where defenses could concentrate. But Bailey bridges allowed Americans to create crossing points almost anywhere. The predictability that defensive planning required disappeared. Defenders had to spread forces to cover all potential crossing sites because bridges could appear anywhere within hours. Post-war analysis revealed production numbers that explained American bridge capability. During World War II, over 490,000 tons of Bailey Bridge components were produced. This represented approximately 200 million linear feet of potential bridge capacity if laid end-to-end. The sheer quantity meant American forces were never limited by bridge availability. If engineers needed bridge components, they were available. German bridge equipment production was approximately 1/10 of Allied production. This meant German engineers operated under resource constraints requiring careful prioritization. Bailey's simplicity enabled mass production. German specialized systems required precision manufacturing that limited production rates. The human element in Bailey Bridge success deserves recognition. American engineer battalions took pride in construction speed. Units competed to set records for fastest bridge construction. This competitive spirit was enabled by simplicity. If bridge construction required expertise, competition would have been dangerous. But because competence sufficed, competition improved speed without compromising safety. Private First Class David Turner, engineer with 291st Engineer Combat Battalion, recalled Rhine crossing in 1989 interview for Veterans History Project. We knew we were building something important. That bridge would get armor across Rhine into Germany. We trained for months on Bailey construction. By March, we could do it in our sleep. When we started at Wessel, every man knew his role. We worked through night, rain, German artillery. Panels went up fast because we'd done it so many times before. When first tank crossed, we cheered. Then we started disassembling another bridge downstream to rebuild it forward. That's how we thought. Build, cross, dismantle, move forward, build again. Bailey made it possible. Today, Bailey Bridge principles remain standard in military bridge construction worldwide. Modern military bridges use updated materials and designs, but follow Bailey's modular, standardized, rapid assembly concept. The British Army still uses Bailey-type bridges. American military uses medium girder bridge, essentially Bailey bridge with updated components. At the Royal Engineers Museum in Gillingham, England, original Bailey Bridge panels are displayed alongside photographs showing Bailey bridges in service worldwide from 1943 to present. The continuity is striking. The same basic design served in World War II, Korea, Vietnam, Gulf War, Afghanistan, and continues in service today. Few military equipment designs have shown such longevity. A museum display explains Bailey Bridge impact with clear assessment. Bailey Bridge was perhaps Britain's greatest engineering contribution to Allied victory. It wasn't sophisticated. It wasn't revolutionary in concept. It was brilliantly simple. That simplicity enabled rapid construction by average engineers with minimal training and standard tools. In warfare, where speed determines outcomes and losses are inevitable, simplicity that enables speed is genius. The broader lesson extends beyond bridges. Engineering often emphasizes optimization, precision, sophistication. But sometimes the best solution is the simple solution that works adequately in all circumstances rather than perfectly in specific circumstances. Sometimes standardization beats specialization. Sometimes easy beats fast, because easy inherently creates fast. German engineering was excellent, precise, sophisticated, optimized. But German engineering couldn't build bridges as fast as Americans needed to cross rivers. American engineering was simpler, less precise, less optimized. But American engineering could build adequate bridges fast enough to maintain offensive momentum. In war, adequate and fast beats perfect and slow. The Bailey Bridge taught military engineers worldwide that sometimes you don't need the best solution. You need the fastest adequate solution. Sometimes genius is making the problem so simple that solutions become obvious. Donald Bailey didn't invent bridge technology. He simplified it to the point where average engineers could build bridges in hours. That simplicity changed warfare more than any sophisticated design could have.